Thank you. Right. So it's host the room. You can really shut off any participant of your choice. Very good. Thank you. Usually I try to start all my talk by saying that it is because the occasion. Obviously, it is not the case here because all of us hope that this day will not come at least for a few more years, but eventually it comes. It comes for everyone. There is little we can do about it. And so just as you have said, the best thing we can do under the circumstances is to try to spend these 2 days remembering life and work of Sergei Ivanovich. And for
Yes.
Yeah. Oh, I see. I will try not to do it again. So for my presentation today, I have actually volunteered to talk about Adyana-Rabina theory, and mostly because I was afraid that it will somehow fall between the cracks. So it may be not the first, the most important achievement of Sergei Ivanovich, and there will be a few talks both today and tomorrow about the on-site problem and related stuff. So it was obvious that it will be covered. This is a very cool result. I really like it, and I will try to convey my feelings today. Why I like it, I mean, Adyana-Rabina theorem. It's maybe not as difficult, but it's beautiful. It has connections, and what is more important is that what is also important is that it actually was the first result that essentially started the path of Sergei Ivanovich on what was to become the passion of his life, which is combinatorial group theory and algorithmic problems in algebra and logic. Right. So let me confess that somehow it is not so easy to talk about events, and I will also say something about the history. It's not so easy to talk about events that happened before born, but fortunately there are good sources. There are very good sources that can. Let's check. So it's technical. So there are good sources, and I mostly consulted this survey paper by Adyan, and also our article we wrote to his 75th birthday. And so this article, obviously, it was discussed with Sergei Ivanovich. So what we have there is more or less authentic. I will follow these two sources mostly, and these are original papers where what is now called Adyana-Rabina theorem was proved short, it was customary, and it's customary short announcements in the doklady, and then it was followed by a big text with complete proof. And also, before we start, let me also mention that so let me also mention that actually the very first paper of Adyan. Before that, he had worked in descriptive set theory, and they actually also have a paper with his teacher Monica. Somehow it changed. At some point it changed, and my talk is precisely about this particular point where it will. It's a bit of advertisement for our article that we wrote. I really recommend to read it if you have not done it already. It has sort of human touch to it, so lots of personal stories. The editorial that will appear in several months in Russian Mathematical Service will be much more scientific according to traditions. So that basically I really recommend to read it. And let us now chat. Yes, I will try. Is it is it better now? I just moved a bit closer to the microphone. All right, good. So let me start, and let me also warn you that in fact we are a big crowd, more than 100 people. Not all of us are experts in combinatorial group theory. So I will really go slow and. My apologies to experts that we also hear. I will try to explain the most basic things. And let me start with a bit of the context. So here it is. It was the time I'm talking about. It was a wonderful time for algorithmic problems. Things just started to appear. It was not very long, or it was not very long yet after the very concept of computability had been developed. But let me start with something which is more or less close to the point. So let us. In 1947, Markov and Post independently wrote the following major results. Let me fix some notation. Sigma is a finite alphabet. So sigma star is the set of all finite words. And let me mention that Sergei Ivanovich really hated when people called words or strings. Please, for speakers, you know this, but never call a word a string, just in respect. So Sergei Ivanovich Adyan. So it's a set of all finite words under concatenation. This set of words makes a semigroup, which is called free semigroup, and then we can impose some relations on this semigroup, which basically means, in combinatorial terms, it means that we can switch from one word over here, and you can do it in both directions. That's actually the source of complications, and it is absolutely basic result, which is called Markov-Post theorem, proved in the same year. And it says that there is no algorithm that decide, given a couple of words x and y, whether they are equal in by or not, or whether you can transform one into another using a sequence. So, and it is called word problem. So far, it's about semigroups. Now, a very interesting question on which Sergei spends quite a bit of time is how many relations do you need here to make this work? And it is a wide open problem. What will happen when one relation, and Adyan indeed spends significant time on this problem. But since Victor is going to tell us tomorrow about it, let me not waste time here and let me delegate it to him. Let's move to groups, because groups is our main subject today. So, and similar programming groups, it looks very similar, but actually it is way more complicated, much more complicated. It was solved by Dr. Serov, teacher, and long time, I think I can say long-time friend. Lifelong friend. I mean, and again, it was an announcement in 52, and full text appeared in 55, and then it was, I think, independently rediscovered by several people in the West. And essentially, it is just the same result. As I said, the proof is way more complicated and uses lots of new techniques. I think that we will see some of those techniques today, I hope at least. And so now we work in the free group. So we consider this alphabet, just take our sigma and add all formal inverses to generators in this alphabet. Again, we look at the words in this alphabet. And if you want a fancy definition, then you take the free group generated by A1 and factor it out by these relations, or combinatorially, if you want to connect it to semi-groups, then what you do, you just insist that you always have, in semi-groups, you always have these default relations that those products are equal to 1. So, and the result is the same. I mean, it is formulated in the same way. So in red here, I have indicated in red the differences. We have larger alphabets, and you don't need to carry the right-hand side because you can always move it to the left now in groups. And the result says that word problem groups is anti-sidable. It's a great result. In particular, Novikov got well-deserved Lenin Prize for this result, and it is absolutely great result. So, and it's introduced lots of interesting concepts. And one remark that I also want to make is that in both results, actually, they are non-uniform, I think. I should call them non-uniform in the sense that you can think that you have a fixed semi-group or group pi, and it is completely fixed, and the algorithm is given only words XX in the group case, or X and Y in the semi-group case, and even that will be acceptable for a particular fixed group G. So let us now slightly change the gear, and instead of working in a fixed structure, let's try to vary our structure a bit. Let's change the structure, and I would now like to make a digression and show you a result in a slightly different area, but which is more or very similar to what we will be discussing today. So it is a very important base theorem in the computability theory. So words in a finite alphabet, they can encode everything you want. In particular, they may encode Turing machines or computer programs, and we introduce the equivalence relation on those programs, and we say that two words are two programs are simply equivalent if they compute functionally, if they compute the same partial function, partial because it's a computability theory, it must be partial. And if we have a property of words or language or predicate, whatever word you like, then we call it abstract or invariant if this predicate depends only on what the program does, not on how it is written. And it is non-trivial in the obvious sense. Then it is an extremely important result. It simply says that if you have any absolutely any whatsoever invariant non-trivial property, then it is algorithmically undecidable whether a given word or a given program satisfies this property. Absolutely. So it's a strong result, and let us now see what we can do for groups here. I will now talk only about groups. So naive attempt to generalize this theorem would be, first of all, we can define what does it mean invariant property just in the same way, because there is well-defined notion of isomorphism for groups, non-trivial, also defined in the same way, and I would prefer to fix this notation. So we have a group G0 that does not satisfy this property, and G1 that satisfies it, and so it will simplify my presentation if we always assume both of them. So all properties will be assumed invariant and non-trivial. The notation G0, G1 is also fixed. And also, I would like to say that I would like also to mention that all my groups will be, all my groups will be finitely represented. A group that has a representation like that, it is called finitely represented, and it's very important that the number of generators is also finite. Most results, they will become easy or trivial without this restriction. So turns out that even with this naive attempt, it is not so easy to explain why it does not work. And here is essentially the only explanation I am aware of. I don't know, it is from Adyan's paper, the one I'm talking about. And it is, if you try to come up with a property, then what you can say that the abilization or the fact that G coincides with its commutant, G with its commutants, or you can write down an arbitrary property or any reasonable property about this factor group, and it will be the reason that it will, after everything commutes, it reduces your problem to a problem about lattices, and so we know everything about lattices we may want to know. So, and turns out that it can be fixed, and the way to fix it is to require that our property or downward closed, anti-monotone, or you name it, whatever you like, in the sense that if H is a subgroup of G, then the property for G implies the same property for H. And so there are many properties like this. Here I listed a few prominent examples. You can come up with other examples. Many properties of groups, abstract properties of groups, they are hereditary because, in a sense, if you go to a subgroup, then it will make your property only, it will make your group only simpler. So, and now we can actually do even slightly better than that, which leads us to what is called now Markov properties. So let me confess that under the circumstances, I was not able to find Markov's paper. It is several pages note in Доклады, and it claims lots of great things. So I was not able to find it. Let me not comment on it. It is called it is called Markov in the literature. So, and what we do, we don't touch G1. G1 is just a positive example, but what we require from a negative example, we relax it. We make it stronger. Namely, we require that if G0 is included into any group H, as always finitely represented, then not only G0 does not have P, but also H also must not have P. And this definition is, as of now, it is asymmetric. And it is also obvious that every hereditary property is actually Markov. You can take just an arbitrary G0, and here we have more examples, either trivial or less trivial. So it's a theorem about hyperbolic groups, about residually fine groups. It is easy remark, but you have to think about it. And simplicity is another example of Markov properties. There are lots of Markov properties. So, and now I have decided to formulate the theorem I'm talking about, and for the rest of the talk we will discuss it. So the theorem is very simple. It is extremely general. It's beautiful. It's general. It says that any Markov property P is algorithmically undecipherable. The statement is here. So let me remind that we assume a priori that G is P is both invariant and non-trivial. And if it is additionally Markov, in particular, if it is hereditary, then it is algorithmically undecidable. So let me now give you a bit of history before we discuss this theorem. And I also should admit that I would probably not do it this way if Sergei Ivanovich would be in the room, but cut away mice to play. So as I said, Sergei Ivanovich started in descriptive set theory, and Novikov, it is Petr Sergeyevich Novikov, suggested to him for his PhD thesis that he does the triviality problem, or it does not mean the trivial problem, it means the problem of deciding isomorphism to the trivial. And this actually, it is oversimplification, because at that time, Adyan already had been familiar with combinatorial group theory. It's him to study a completely new area. He had been familiar with this. And this is his answer. He reminds that we are working with finitely representable group. We are not interested in any others. Well, with one exception. And isomorphism problem, not only to the identical group, but actually to an arbitrary fixed group. And somehow it is a separate theorem in the paper, and from personal communication with Adyan and from our research, that somehow he thought that I mean in this paper or in his PhD thesis, somehow at that point probably the importance of what is called Markov property was not so. He just solved isomorphism problem, and yes, here is theorem number 2. It's more complicated statements. So it is here, and let remark what I put here Markov in the parentheses. The reason is because I hope that it is clear that at that time this term did not exist, Markov property. Maybe it should be actually Markov Adyan property. That would be very natural. And also the same goes for many things I already mentioned in my presentation. One has to remember that at that time, most of those concepts did not exist yet. So then the next episode, this is Yesenin Volpin. So he was the official opponent of Sergei Ivanovich's thesis. And he said that, all right, it must be doctoral, or for those who don't know here, it is the Russian analog of German habilitation, roughly the same level. And that was Novikov's response. And as we all know, and we are going to hear about it in the next talk, it was fully realized very soon. And the conclusion of the story was that Maltsev was the leading organization, almost everyone here knows what it means. That at least it should be, we should mention somehow that it is PhD with special distinction during the defense. I don't know if it was ever done, but anyway, so that is the story. And for those of you, and most of you know a bit of the Soviet history, so all these individuals, they had very different position on the Soviet government. And what unites all of them on one slide is the fact that they liked very much Adyan's thesis, and that might be about the only thing they agreed on. All right, anyway, about the history, and in the remaining 50 minutes, some science, some speculations or ramifications. Whatever about Adyan, I will try to explain why I think it's a great theory. So let us, as I mentioned, the property of being Markov is inherently asymmetric, G naught and have very different rules. However, the conclusion is symmetric. So let's also make the assumption symmetric also. And it is the notion P-forcing group. So it is a group it is not have the property P, but every group into which it may be embedded will have the same behavior. Then Adyana-Rabin theorem in these terms, it can be reformulated as saying that if we have any P forcing group in either direction, then it is undecidable, and it is very interesting to look at the contrapositive of this statement, which simply says that if P is decidable, then there is no P forcing groups, and so it is quite remarkable because now it is quite remarkable because on the left-hand side we have purely logical statement, and on the right-hand side it is absolutely algebraic statement. There is nothing about computability here. So let us look at the only example we know of this property, of a decidable property. For example, G, the abilization of G is trivial. It is obvious that how to spoil this property in any group, or you simply say add Z to it. And it is very good exercise. I was not able to do it. I actually asked for Igor's help. So it follows from, formally follows from Adyana-Rabin theorem that you can also spoil, you can also kill the abilization. So for any finitely presenting group, you can also finitely, FP is the same as FR, finitely represented. So you can embed it into a group with trivial abilization, and it's a good exercise just to try to do it. It is not very difficult if you know a bit of combinatorial group theory, but it is by far not trivial, and this is very important for this exercise, that it is actually finitely presented, not only finitely generated. It's finitely generated, it is easier. And as I said, I am not aware about any other very different examples. So all other properties, they are more right. You can probably find variations on this, but it's open-ended question that I think is very interesting, very important. Are there any other properties that are decidable and so that are based on different principles? So if anyone has suggestions, then please put them on the chat, and we will have more fun then. Right, good. So this is the picture. It's symmetric Markov properties, and we have lots of stuff here. Then it is included into undecidable properties. It is Adyan theorem. These are all non-trivial properties, and this gap between undecidable and non-trivial is let's look at this gap. So are there any undecidable properties that are not symmetric Markov? Turns out that it is also not easy to find these things. So, the first example, which was actually not an example at the time, I remind that this part of my cartoon. So, and as I already mentioned in Adyan's paper, isomorphism, Markov or Markov-Adyan properties, it were to separate different theorems. So, and of course, the question is why. So, finally presented group, we can always find G that is not embedded into it. So, obviously, isomorphism cannot be forced. You can always spoil it. Non-isomorphism. So equivalently, does there exist a universal finitely representative group such that every other subgroup, every other group can be realized as its subgroup? This question is turned out to be very difficult. It does follow from Higmann's embedding theorem that appeared several years later. I am pretty sure that Adyan-Rabin theorem was very significant reason why people even started to think about these directions. So it turns out that this group actually exists universal group, the isomorphism. So this group is not Markovian, is not Markov property. And so it is also a very remarkable result, both Higmann's theorem and this consequence, because as far as I know, it's again pure algebraic facts, and again, to the best of my knowledge, we don't have any proof of this statement that would be purely group theoretical or purely algebraic. So universal groups are more like unicorns. So are there any more practical examples? Practical, whatever you mean by this, more natural examples? Again, I know only one. So, and it's an important concept in group theory. It actually came from topology. A group G is a half group if every epimorphism from G onto itself is actually an isomorphism. If you take any non-trivial factor of G, it is not isomorphic, or is it not isomorphic? It may not be isomorphic to G. Again, like any good thing in life, being Hopfian is easy to spoil. The question is whether you can spoil the opposite. And here are two results. Both are very deep, and the order of appearance. Collins proved that this property of being Hopfian is algorithmically undecidable, so which means that it does not reduce to Adyan-Rabin theorem, and only several Years later, Miller and Schlup, they proved that actually it is not a Markov property, which means that if I have a finitely representing group, then I can always, even if it is Hopfian, then I can always, even if it is non-Hopfian, then I can make it Hopfian by embedding it into something else. So all these things are non-trivial. Let me go back for a second. The bottom line is that on this slide, really, almost everything is symmetric Markov, either the property itself or its complement is Markov, which is not so easy to come up with any examples. So Adyanar-Rubin theorem is a remarkably general statement. So, such it is. It was highly evaluated by the community. So let me now talk very briefly, because I don't feel myself competent to talk here much about it, about the main application of this theorem. I mean, outside of group theory, in group theory, it's a major result, classical result, but probably the most known application outside group theory is it was given immediately by Markov. So, and so it says basically that homeomorphism, as he called it, problem, so manifolds is not decidable in dimensions beginning with 4. And this proof, and what I will show on the next slide, it uses Adyanar-Rubin theorem, and moreover, it uses some other more technical concept. I don't have time to talk about it here, which is called Adyan sequences. So something which you can extract from the proof of this theorem. It is not taken as a black box. And there is very little, there is actually very little we can add to this theorem by now. So as for K. Petrovich Novikov, it's not Z. Novikov, it is his son, famous topologist and mathematical physicist. He proved that actually in dimensions beginning with 5, which is you can take as m to the n, you can take the most famous manifold, which is the sphere, of course. So Stanko had a paper where he basically explained what Markov had in mind. So it is a very good expression of this theorem, but what happens in dimensions for 3-dimensional manifolds, it is big open problem. There is lots of research done on it, but it is still wide open. And so I think we will not go to the proofs. In my remaining time, let me also talk about something more very similar and beautiful conjecture, which is still open in my own area, well, current area, I mean, complexity theory. So we can apply the same paradigm as we did before. So many different objects. We started with the Rice theorem, which was about programs. Then we moved to groups, Adyanar-Rubin, and let us now consider graphs. So what is invariant, it is clear, because for graphs we have quite well-defined notion of isomorphism. And also, you know what is hereditary, it is anti-monotone, or let's better take monotone. It is not important, of course, in what direction we go. Well, the question should be asked to be considered, because now all these objects are completely finite. You can decide everything. And in fact, many things, not all of them, but many things, you can also decide in polynomial time. And so it is also too strong to ask meaningful questions. I mean, general questions as general as Adyanar-Rubin theorem. So let me now remind you, let me now remind you this was still extremely important computational model. It's just decision tree model. So what you do, you query pairs of vertices V of G, and you get an answer to your query whether UV is an H or not. And what makes it interesting is that you do it adaptively, which means that your next query, it may also depend on the results of your previous query. We look at worst case complexity. You can be lucky, but we assume that we are interested in the minimal number of queries that you need to ask, no matter how what is for any input, regardless of the input. And if Asm is conjecture, it will solve for or semi-solve for many different similar problems. And there are partial results about this one. It is remarkably similar. Again, I am not sure if there are any formal similarities, but at least it is remarkably similar to Adyanar-Rabin theorem. It simply says that if you have any non-trivial and invariant, that's always monotone property of graphs, then you are really in deep trouble, because the best you can do is just query all and choose two possible pairs. In the worst case, you will need as many queries as you do with the trivial algorithm, that just asks about all the pairs. And here is a very interesting and striking result about the when n is the power of a prime, and the proof is also very interesting because it uses non-trivial topological methods and quite non-trivial algebraic topology. So graphs first it generalizes the problem to more general situation, and then it works with simplices, but the general conjecture is still open. And as I said, it is remarkably logical to Adyanar-Rabin theory. Right, so that's the end of my slides. My time is almost up. I think I will not say much about the proof of the theorem. So, but I think I will just, in the remaining time, in the remaining minute, I will just say a couple of words. What you do, you apply to, you have to, so constructions in combinatorial group theory, very basic construction, which is amalgamated products and what is called H and N extensions. And H and N extensions, they were independently rediscovered what was different by Dr. Sergei Novikov for this work, and it was called Проходная буква. I don't know how to say that in English. So you need these two constructions, and then what you basically do, take any from Novikov's theorem, you take any group H in which the word problem is undecidable. You take these groups G0 and G use a word problem in H. So your Markov property, it's a very clever reduction, but it is basically based on the observation that with respect to that these two constructions and amalgamated products, they behave very different with respect to whether an elements to which you applied them is one or anything that we actually need for this reduction. Details here are slightly complicated, so I will not here. I actually didn't expect that I will have time, so let me stop here. It's a great result, and so it's the start of our conference. Thank you.